when we first learned about angles, we learned about a particular unit called degrees. Now, you might remember the little story that I told about how degree measure probably came about, and it's because of the fact that it's very close to the number of days that are in our Earth year. The problem with this unit of measure is that it's a very arbitrary number to use. And if we were to go anywhere else in our universe, it wouldn't really make a whole lot of sense to use degree measurement. So in a lot of applications involving motion and in engineering and in the sciences, we use another measurement called radian measure. And radian measure is actually what we refer to as unitless. We're going to see why it has no particular unit. But the idea is to be able to describe the angle simply by how big the circle itself is, what the radius of that circle is. Let's take a look at the way that we can create this new unit of measure for an angle. So first of all, I'd like you to recognize that this length right here is the radius of our circle. Now, the whole purpose of a radian is to be able to describe an angle as a real number, not in terms of a degree measurement where we're looking at 1/360th of a circle, but instead we're looking at it in terms of how big the circle is itself. So let's picture this radius, this R, this blue line right here, as a floppy string that I could pick up and start wrapping around the circle. Now the question is, where is that radius going to end? And it looks like it's probably somewhere around right here. So if I were to stop this radius wrapping around the circle, that would end up also connecting to the origin, giving me another radius, right? It turns out that this angle formed by mapping one radius around the outside of a circle is considered 1 radian. So what we're referring to here is 1 radius corresponds to the angle of 1 radian. And that's what we refer to here as sometimes as a shorthand notation, 1 rad. Or in other words, just one. Sometimes if you just see theta equals 1 and it doesn't have the little degree symbol up here, then you know that it must be involving or it must be in terms of a radian. So when we think of radians, a radian should be thought of as nothing more than just a piece of a pie or a piece of this rotation where 1 radian is equal to 1 radius. Which implies as well that if I were to take 2 radiuses or 2 radii, that angle would represent 2 radians. And same with 3 radians and 4 radians and 5 radians. So each of these segments here, each of these red dots indicate where the radian will stop being one and start being another. So this is 1 radian, travel through to get another radian, travel around to get another radian, just above 180 degrees. So it looks like half of a rotation is a little bit bigger than 3 radians. And then we get to 4 radians. And 5 radians is going to be somewhere around down here. As you can see in the next diagram, 5 radians. 6 radians will now take us all the way around to almost a full rotation, but not quite. So basically what we're seeing here is that approximately, we could see that there is approximately 6 and a little bit radians in a full rotation. So we can actually find how many radians there are in a full rotation just by thinking about this in terms of the circumference. But one way to think about this is in terms of a proportion. So let's just recognize that 1 radius on the outside of the circle corresponds to an angle measurement of 1 radian. So that should be proportional then to the circumference because if I know that one radius around the outside of the circle correlates to one radian, then going around the entire circle should correspond to some other value of theta. So that would mean that the circumference, or the circumference over theta. All right, so if we were to simplify this a little bit, why don't we think about one radius as simply being r? So let's rewrite this as r, one radius, divided by one radian, which remember it's called unitless, it has no measurement, and therefore that's equal to c over theta. Well, if we were to cross multiply, notice that this would tell us that the circumference times 1 is equal to theta times the radius. So remember, we're just trying to find out what angle or how many radians does a full rotation account for. Now you might remember that there is a formula here for the circumference of a circle. The circumference of a circle is 2 pi times the radius, right? That just comes from the circumference formula. So look at what's amazing about this result. That just simply tells us that one full rotation is equal to, well, 360 degrees. But we also see that that theta must have been 2 pi. So notice that what we're recognizing here is that there is that 360 degrees is equal to 2 pi radians. Now we don't have to write the word rad after it. If there is no degree symbol, then that implies that there is that we are in terms of radians. Now one more very important relationship here, if 360 degrees, if one full rotation around is 2 pi, then that must mean that half of a rotation is simply pi. But we also know that 180 degrees is 1/2 of a rotation. So more importantly, we can see that 180 degrees is the same as pi radians. So now we're going to be able to describe angles within a rotation, not in terms of these large numbers called degrees, but instead we can put them in terms of much smaller values, 1, 2, 3, 4, 5, 6, and so on. Or sometimes we could put radian measures in terms of pi. We can now use this fact that 1/2 of a rotation, 180 degrees, is equivalent to the value of pi radians. That's like saying 12 inches is equal to 1 foot, or 5,280 feet equals 1 mile, or 2 cups equals 1 pint, right? You're showing an equivalency between two different units, so we should be able to create a conversion factor in order to convert from one to the other. So let's say that we want to convert from degrees to radians, okay? That would mean that we start with degrees and we want to equal radians. So we should be able to multiply by something that's going to give me radians and cancel degrees, so that the degrees cancels from the numerator and denominator. So the way that we're going to do that is by simply multiplying by the conversion factor of converting from degrees to radians would give me pi radians divided by 180 degrees. So just be very careful to recognize that this is actually equal to 1. Pi radians over 180 degrees is the value of just the real number 1, because these are actually the same thing. So if we want to convert from radians to degrees, we're just simply going to multiply by 180 degrees over pi radians. which of course is also equal to 1. So this conversion factor will allow us to convert back and forth between the two units. So we should now be able to look back to this last diagram on the 6 radians and recognize why pi radians make sense. Why is it that 180 degrees is actually the same as pi? Well, remember that pi is 3.14 approximately, which also means that 2 pi is 6.28 approximately. And so it should make sense that if we've traveled through 1 radius, 2 radii, 3 radii, and we're still not to halfway, we just have to travel a little bit further in order to get to 3.14 radians. We continue to travel around to 4 radians, 5 radians, 6 radians, and now we just have a little bit extra, which turns out to be approximately 0.28 radians to account for the 2 pi radian total. Okay, so let's go ahead and take a look at a couple of examples. Whenever possible, we would like to keep our radian measures in terms of pi, because you'll see very shortly that this will be a much easier way to locate where they are on our circle. But let's start with 150 degrees. So this is a standard degree measurement in the second quadrant, just a little bit less than 180 degrees. And we want to convert this into a certain number of radians. So remember, what we're going to need to do here is cancel out the degrees. So that means we're going to have to multiply by a conversion factor where the degrees cancel. So that must mean that the 180 degrees goes on the bottom while the pi radians goes on top. And therefore, when we multiply those, that ends up giving me 150 pi over 180. And notice that there's no degree symbol anymore because the degrees canceled. But notice that we're always able to simplify that a bit more as well. So we could simplify that by dividing out a 10. And it gives me 15 pi over 18. But I'm still not finished until I simplify that even further and recognize that 150 degrees, if I cancel out a common factor of 3 from both, gives me the radian measure of 5 pi over 6. So we're able to leave it as is. 5 pi over 6 is the radian measurement. Now we could convert it to a degree. I'm sorry, we could convert it into a decimal, but it's not necessary to convert into a decimal simply because of the fact that putting it in terms of pi is going to be more beneficial to us in the end. So let's go ahead and do that same idea here and turn 9 pi over 4 radians into degrees. So we want there to be a degree symbol over on the right side. Well, same idea, but notice the only difference now is that the thing that I have to multiply by is going to have to cancel the radians, which means that the degrees is going to have to go up top. So the conversion factor is 180 degrees for every pi radians. And now you should notice that not only does the radians cancel, but the pi cancels as well. And so now, just to make this easier without actually multiplying it out, okay, I'm going to leave this as 9 times 180 divided by 4. And the reason I'm doing this temporarily is just because oftentimes the denominator will go into 180 instead of having me multiply 9 times 180 to get a massive number. So instead, we could see that 4 goes into 180 45 times. So what we're left with is 9 times 45 degrees, which means that if we look at 9 pi over 4 radians, that's going to be equal to 405 degrees. Notice that's a little over 360. But that makes sense because if you take a look at 9 pi over 4, that's a little bit bigger than 8 pi over 4. 9 pi over 4 is a little bigger than 8 pi over 4. And notice that 8 pi over 4 is 2 pi. So it makes sense that 9 of those pi over 4s is going to be larger than 360 degrees. Now we could convert this into decimals, but we don't really want to do that unless the simplification doesn't work out nicely. Before moving forward, I want to just demonstrate real briefly the difference between 30 degrees and 30. So 30 degrees is not equal to 30 radians. 30 is a real number. It's a real amount of radii that has traveled around the circle. Degrees is just an arbitrary measurement. So there's a real big difference between calculating sine of 30 degrees and calculating, say, sine of 30. This is why I've been very particular so far in our videos to make sure to put that degree symbol every time we put an angle inside of our trigonometric function. Because if that degree measure isn't there, then that implies that 30 is a radian measure. And just look at the big difference between 30 degrees, which is in the first quadrant, and 300 degrees, which travels around once, twice, 3, 4, almost 5 times around the circle. So be very careful with the difference between degree measurements and radian measurements. So it's now time to determine some of the most important equivalencies between degree measurement and radian measurement. And the way we're going to do that is by first of all looking at our quadrantal angles, but after the quadrantal angles, we're going to look at our 30, 45, and 60 degree angles in each of our quadrants. So let's start off with our quadrantal angles. Okay. So our quadrantal angles are obviously 0 degrees here, and half of a rotation is 180 degrees over here. Now, half of 180 degrees is obviously 90 degrees. So when I'm writing these angles on the outside of the circle, what we really mean is that this angle is 90 degrees. This angle is 180 degrees. So each quadrant is 90 degrees, so that must mean that this third quadrantal is going to be 3 90-degree angles, or 270 degrees, until we finally get around to 360 degrees again. Now this is a great point to start because this is going to now be able to see that 180 degrees is equivalent to pi radians, and 360 degrees is 2 pi radians. Now again, what that means is that this angle is pi radians, which means another pi radians, meaning the bottom half of the circle, takes me around to 2 pi radians. But the beauty of keeping things in terms of pi is that we could realize that all of these other angles that we're going to create are nothing more than fractions of that half turn, or fractions of pi. So notice how in this top half of the circle, this whole top half of the circle, there's actually 2 pieces. This is half of the top half, and this is the other half of the top half. So that must mean that 90 degrees, since 90 degrees is half of 180, 90 degrees is actually half of pi. We're going to write half of pi as pi over 2. So just keep that in mind, right, in terms of algebra, that if I have 1/2 of pi, that's obviously equivalent to pi over 2. And likewise, if we have pi over 2 and another pi over 2 and another pi over 2, then that's going to give me a total of 3 pi over 2, or 3/2 of pi. So in other words, 3/2 pi is 1/2 of pi. So now let's take a look at cutting each of these quadrants in half. So we have now created a 45-degree angle inside of our first quadrant. And the reason is because I cut the 90-degree angle in half. But notice that I cut every quadrant in half, so that must mean that each one of these is 45 degrees. So if we move our way around this circle, we could fill in what the 45-degree reference angles are in every quadrant. Because remember that a reference angle is always based off of its proximity to the x-axis. So this is 45 degrees, this is 45 degrees, but this is also 45 degrees, and that's also 45 degrees. So these are all of our reference angles. So if we continue to move our way around, 45 plus 45 gives me 90 degrees. 90 degrees plus another 45 gives me 135 degrees. If I add another 45, I'm now at 180. Keep adding 45, this gives us 225 degrees. Add another 25 to get to, add another 45 to get to 270. Add another 45 to get to 315 degrees. And if I add another 45, I'm right back to 360. So these are all the important 45-degree reference angles in each of our quadrants. But now we want to convert this to radians. So let's think about this again. I've taken 90 degrees and cut it in half to get 45. So that must mean that I need to take half of pi over 2. I need to multiply pi over 2 times 1/2 and realize that that's now pi over 4. So 45 degrees is now, from this point on in this semester and all other classes involving radians, 45 degrees is the same as pi over 4 radians, which is pretty great because now I'm going to be able to convert all of these other 45-degree reference angles into radians as well. Well, let's count again. Since this is 1 pi over 4, in other words, this is pi over 4, and this is pi over 4. We could see they're all the same size, right? They're all the same size. By the time we get around to 135 degrees, we've gone through 3 of those pi over 4s. And here's another pi over 4. So by the time we get to 180, we've gotten to 4 pi over 4s, which totally makes sense because 4/4 is 1. Which means we add another pi over 4, and now that means that 225 degrees is 5 pi over 4. This is something that we don't want to have to memorize, but instead understand how to create this. Add another pi over 4, and we're now at 6 pi over 4. But notice 6/4 simplifies to 3/2, which is why it's already written. And finally, we keep adding pi over 4s to get us to 7 of those pi over 4s. And by the time I add 1 more pi over 4, I'm now at 8 pi over 4, which sure enough is 2 pi. So why don't we take a look now at drawing some 30-degree angles. I've now drawn some green lines that are going to represent our 60-degree angles. And the reason for this that you can hopefully see if you try to disregard the red ones is that this whole piece right here is going to be one part of 180 degrees. This will be the exact same size, and this will be the exact same size. So if we disregard the red lines or the red angles, we can now see that we've cut 180 degrees into thirds. So 180 degrees divided by 3 is going to give me a total of 60 degrees. Which means if I just start adding 60 degrees to move my way around, then 60 plus 60 gives me 120 degrees. And add another 60, it now takes me to 180 degrees. If I now add another 60, that takes me to 240 degrees. add another 60 to take me to 300 degrees. And finally add another 30, or 60 rather, in order to take us to 360 degrees. But what you should also recognize is the symmetry involved. Remember, with reference angles in each quadrant, if this right here is a 60-degree reference angle, then 60 degrees from the x-axis in the second quadrant is also a 60-degree reference angle. And this is also a 60-degree reference angle, and this is also a 60-degree reference angle. So we're going to see something very interesting about the radian measures in 1 second. So let's take a look at how we can work this out. If 60 degrees was 1/3 of 180, then 60 degrees must also be the same as 1/3 of pi. So let's work that out again. 1/3 of pi is simply pi over 3. So 60 degrees is pi over 3. 45 degrees is equivalent to pi over 4. 90 degrees is equivalent to pi over 2. So now if we do that same thing as we move around, start adding pi over 3, and this is pi over 3, and this is pi over 3, and this is pi over 3, and so is this, and so is this, and so is this. So there should be 6 pi over 3s by the time we get around to 2 pi. So we just want to fill in what our degree measurements are as radians. So pi over 3 plus pi over 3 means that 120 degrees is 2 pi over 3. Add another pi over 3, which means that pi radians is 3 pi over 3, which makes sense because that's equivalent to pi. Which means that 240 degrees is equivalent to 4 pi over 3. And finally, 300 degrees is 5 pi over 3. So we're just counting the number of pi over 3s until we finally make one full rotation, which is 6 of those pi over 3s. So we now have some very intriguing patterns that start showing up here. So before we move on, let's take a look first. Let's look at all of the angles that are halfway into the quadrants, all the 45-degree reference angles. I'd like you to take a look at all of their denominators. If a radian measure has a denominator of 4, it must be equivalent to a 45-degree reference angle. If, on the other hand, you see that the denominator is 3, look at how all the denominators of 3 are 60-degree reference angles. So if you start referring to something like 7 pi over 3, you know that it's going to be a 60-degree angle. You just have to determine which quadrant is it going to be in. So the last special angle we have to deal with is a 30-degree angle, so let's go ahead and draw those. Let's take a look at how we know that this is a 30-degree angle. Okay. There's a few ways visually to recognize this, but we could first of all see it as one 30-degree angle being equivalent to another 30-degree angle, which is equivalent to another 30-degree angle. So 1/3 of 90 degrees gives me 30 degrees. Another way to see this is that the distance from 45 degrees to 60 degrees is a difference of 15 degrees. So 15 degrees on the opposite side should take me down to 30 degrees. So this is one way to recognize that the 30 and 60 degrees are not cutting the 45 into halves, right? They're breaking it into thirds here. So now we'd like to take a look at all of the measurements of 30 degrees as we move around. So again, we could start counting. We could say 30 degrees plus 30 degrees gives me 60 degrees. 60 degrees plus 30 degrees gives me 90. 90 degrees plus another 30 gives me 120. 120 plus another 30 gives me 150. And by the time I add 30 degrees more, I'm now at half of a rotation. So we can still add 30 across to get 30 more to get 210 degrees. But another way to do this a lot faster is just to realize that each of these angles are 30-degree reference angles. So 30 degrees above 180 or below 180 is 150. 30 degrees past 180 is 210. 30 degrees before 360 must be 330 degrees. So the first thing to make sure we're familiar with is all of these special, there's 16 special degree measurements on this circle. All of the quadrantal angles, but in addition to that, all of the 30, 45, and 60 degree reference angles. But let's take one last step and turn the 30 degree angles into radian measure so that we can see all of the special radians that are going to continue to pop up over and over in trigonometry. So a few ways to go about this. We could see that 30 degrees is 1/3 of 90 degrees. So 1/3 of 90 degrees is 30 degrees. I could also see that it's 1/6 of 180 degrees. 1/6 of 180 degrees is 30 degrees. So either way we take a look at this is fine, but the reason I'm going to look at it in this circumstance is because of the fact that we have 1/6 of 180, which is equivalent to pi. 1/6 of pi gives me pi over 6, which means that 30 degrees is pi over 6. We can now start counting around again, or by the same thing we did earlier, if I know that each one of these reference angles is 30 degrees, then I also know that each of these reference angles must be pi over 6 radians. So if 180 degrees is equivalent to 6 pi over 6 radians, then all I really need to do is take 1 pi over 6 away from 6 pi over 6 to get 5/6 of pi, or 5 pi over 6. And then I could add 1/6 on to 6/6, which means that this reference angle, this angle is 7 pi over 6. And finally, 1/6 of pi, less than 2 pi, but keep in mind what 2 pi is. It's also 12 pi over 6, which means that 330 degrees is 1/6 less, or 11 pi over 6. So I really want to start to take some time here to look at a few really helpful patterns in this figure. First of which, you should see starting at the x-axis, as we move our way up towards 90 degrees in either direction, notice how the denominators change from 6 to 4 to 3 to 2. Likewise back here in the second quadrant, 6 to 4 to 3 to 2. And now if we start moving in this direction, we see 6 to 4 to 3 to 2. And finally, coming down in this direction, 6, 4, 3, 2. So it looks like the denominators decrease in size as you move away from the x-axis. But let's think about why that actually makes sense. It makes sense because of the fact that a 1/6 is smaller than a 1/4. And a 1/4 is smaller than 1/3. And 1/3 is smaller than 1/2, which correlates to the smaller fractions in that region. So another pattern to help yourselves remember is that every one of the numerators in the first quadrant is just pi, because of the fact that it is 1/3, 1/4, and 1/6 of pi. While in the second quadrant, notice how the numerator is 1 less than the denominator. The numerator is 1 less than the denominator. The numerator is 1 less than the denominator. Let's try to understand, instead of memorize, understand why that happens. The reason that occurs is simply because of the fact that I'm taking away 1/6 from pi. I'm taking away 1/4 from pi. I'm taking away 1/3 from pi. So if I take away 1/6 from 6/6, I'm left with 5/6, and so on. While in the opposite direction, I can see that the numerator in the third quadrant is 1 larger than the denominator. The numerator is 1 larger. The numerator is 1 larger. And that even happens right here. The numerator is 1 larger. And the reason is because I'm starting with 6/6 and adding an extra sixth. I'm starting with 4/4 and adding an extra fourth to give me 5/4. I'm starting with 3/3 of pi and adding 1 more third of pi to get me to 4/3 of pi. So this is a really helpful tool to help you see what or remember what the radian measurements are as well. But what about the fourth quadrant? It's a little trickier. But one thing to recognize is that if 2 pi is 12/6 of pi, 11/6 is 1 less. I see that 2 pi is the same as 8/4 of pi. 7/4 of pi is 1 less. I see that 6/3 of pi is a full rotation, so 5/3 of pi is 1 less. So essentially, we just got to realize that each of these can be found using our reference triangle or our reference angles. Another pattern that you might recognize is that every time you start with any angle, let's say we started with this angle, and take 1/2 of a rotation to the opposite side, not only do I know that that's pi radians apart, but I also see that the denominators are the same, which shouldn't really be too surprising if you recognize that in order to move from 5 pi over 6 to the opposite side, I have to add 5 pi over 6 plus 6 pi over 6, which gives me 11 pi over 6. And that'll happen anywhere on this circle. That's why you could follow the blue line all the way across, or the red lines or the green lines all the way across, because those are always going to be pi radians apart. But whenever you see the radian measurements written in terms of 5 pi over 6, just keep in mind that that's saying that it's a fraction of pi. So 5/6 of pi could be written the same as 5 pi over 6, and I should see that 5/6 is less than 1, so it's less than 180 degrees. Or if I look at 5/4 of pi, 5/4 is bigger than 1. So I know that's going to be not only written as 5 pi over 4, but I also know that it's going to be past 180 degrees. Now you should really try to learn these equivalencies as soon as possible. Even though we're going to be able to take an intermediate step to convert radians into degrees, and a lot of students are typically resistant to radian measure when you first learn it, but it turns out to be an extremely important aspect of trigonometry. And oftentimes students that are even in calculus can't tell me where 3 pi over 4 is. Instead, we want to make sure that we understand how these are fractions of pi and reason through without having to convert to a certain decimal value, or I'm sorry, a certain degree measure. However, let's go ahead and take a look at an example of what we can do. We will now start seeing trigonometric functions with radian measurements as their angles instead of degrees. So right now, we can convert 2 pi over 3 radians into degrees by simply multiplying it by 180 degrees over pi radians. And when we do so, notice that the pi cancels out, and we're left with cosine of 2 times 180 over 3 degrees. Well, if 3 goes into 180 60 times, 60 times 2 gives me 120. And therefore, what we're really doing is calculating cosine of 120 degrees. But we're still not done because we still have to be able to calculate what that cosine value is. And so why don't we take a look at this circle again. Now, when we looked at 2 pi over 3, we should have been able to already recognize or start getting closer to recognizing that we're referring to the 120-degree angle. And just a few things to keep in mind. Since it's got a denominator of 3, I know that it's going to be furthest from the x-axis. Then I just got to think, well, 2/3. 2/3 is less than 1. So I know it can't be the first or third quadrant, or the third or fourth quadrants. And since the numerator is 2/3, that's 1/3 less than 3/3. So you should already be able to start thinking through where this is going to be, and therefore use this circle. We should now be able to focus only on the location where 120 degrees, or 2 pi over 3 is. And keep in mind that what we're trying to do here is find what is cosine of this 120-degree angle. Well, if you remember what we did before, we then had to drop a vertical down to the x-axis to form a reference triangle, and realize that if it's a 120-degree angle, or a 2 pi over 3 angle, that this is actually going to be 60 degrees, or in terms of radians, pi over 3. And because of the fact that this is a 30, 60, 90 triangle now, I can fill in the lengths of my sides by realizing that the hypotenuse is 2, the short side is 1, and the height is √3. This is just our special triangle that we've been using to calculate our trigonometric functions. But be very careful with our signs as well. Since we have gone backwards into the second quadrant, our x-coordinate is -1. Our y-coordinate is still positive because we've moved upwards. So now what we're realizing is that cosine of 120 is the value of x over r from our common ratio, and therefore cosine of 2 pi over 3 is the x-coordinate of -1 over the y-coordinate of 2. And the way that we found that was first converting it into degrees. But very quickly, we want to start to not have to convert into degrees and instead know where we are so that we could still create our special triangle. I'd like to take a look at another example without converting into degrees to now try to think about the logic of the patterns in our circle. So since we're trying to find tangent of -3 pi over 4, I first of all have to think about where is -3 pi over 4? Well, I know that I'm going to be working my way downwards. So I know that negative means that I'm looping around in this direction. I also realize that pi over 4 is halfway into the quadrant. So I know that it's going to be one of those pi over 4s, two of those pi over 4s, and finally, 3 of those pi over 4s. So this angle right here is the angle of -3 pi over 4 radians. So notice that I never had to actually use the convert it into degree measurement in order to find it. We're using the pattern in terms of breaking up pi into a certain number of parts. Now, if I now drop this to the x-axis to form a reference triangle, since it's halfway into the quadrant, I should realize that this is a 45-degree angle. In other words, a pi over 4 angle. So because it's a pi over 4 angle, that means that our two legs are 1 unit each, while my hypotenuse is the square root of 2. Again, that just came from our special triangles. Now be very careful though, again, because since this is in terms of the x-axis and the y-axis, in order to get down into the third quadrant, I had a -x and I had a -y. So in order to compute a trigonometric function here, all we're doing is drawing our reference triangle and realizing the tangent is y over x. Well, in this case, the y coordinate is -1. The x coordinate is also -1. So that must imply the tangent of -3 pi over 4. Notice that we never use degrees in order to compute this trigonometric function, but we see the tangent of -3 pi over 4 is equal to 1. So get very used to these equivalencies and practice real hard to memorize these. But again, it's not memorizing this whole diagram. Instead, it's understanding the patterns and the relationships so that you can reason through where they are instead of trying to memorize this entire diagram.